So very quick introduction just to set the scene. I'm not attempting to tell you what an inverse problem is because you all know what an inverse problem is. But just to set notation, so in what I'm going to talk about, y will always be my measurements. U is the physical quantity, the model parameter that I want to reconstruct, which in my case will be mostly an image. And the forward operator is called capital T, and then I have epsilon for kind of generic random corruptions that I have in the data. Okay, I think actually it's better for me to just stand here and show you this like this. Okay, and then my notation for the pseudo-inverse is this T dagger. And we know that the typical inverse problems that we're interested in, which is reconstructing U from y, are ill-posed. Okay, so this is why they're interesting. And so just to show you the type of inverse problems we are interested in are in particular those in which this forward operator T is taking the model parameter U into a different space. Okay, so U lives in image space, let's say, and the measurements live in a projection space. Which is this one here. So this would be computed tomography. And these are the typical type of problems we want to solve in this presentation. Okay? Good. Now, I said before, these problems are usually ill-posed because of various reasons. If you look at this little demonstration here, one reason they could be ill-posed is because they are underdetermined. So going from right to left is easy. If you know the hand posture, you can predict what the shadow projection looks like. But if you just know the shadow projection without knowing anything else, it's hard to go back. Maybe if you would know something about what has actually produced the shadow, like two hands or something, maybe you could do more. And this is roughly the idea of variational regularization approaches. So you add to this equation that we've started out with, Tu plus epsilon equals y, you add some prior assumption you have about the type of U's that you want to reconstruct that fulfill such a relation. And you cast this in terms of a regularization procedure. Okay? And typical type of regularization procedures that are used in imaging, which is really the type of inverse problems I'm talking about today, are, for instance, the total variation or some generalizations of total variation or many others. I'll get to that later. Okay? So typically we think about this regularizer R as some type of sparsity promoting L1 type regularization. These are at least the kind of successful ones that are out there. And there are many applications. Sorry, I should have gotten rid of this slide because it's usually for people to motivate them that this is kind of interesting. But really the type of inverse problems that this talk is pitched for are really the ones where I'm taking my image U into another space. And in the context of this, thinking about doing this step from measurements to image via something learned might be more challenging because you're switching between two different spaces. Okay, so the title had regularization in it. So what I'm wondering really about is if I start with such a variational regularization approach, how do I choose this regularizer usually? Okay, and the one approach that I will show you is maybe I can choose a regularizer by learning it in a certain way, looking at some examples that I want this variational regularization approach to spit out. Okay, but let's look at some attempts or some things that are really popular in inverse imaging for solving this. So this is just to make a point. My forward operator T is just the identity. So it's an image denoising example just to show you the effect of different regularizers. Again, many of you are used to this. So here on the left, this is my measured image, which is noisy. Here on the right, this is the image U I want to compute, an approximation to the clean image. And I do this via total variation regularization, also via the so-called ROF model. And what I get is a pretty good reconstruction, and it's pretty good in the sense that actually many, many people in inverse problems are using the total variation extremely successfully. If you look at the number of citations that you get for total variation regularization when you type it into Google, it's huge. So it has been really successfully applied, but you can also see, so you can see why, because it really nicely reconstructs sharp edges, discontinuities, it can preserve them. And in many cases where we use images to do some quantification task, this is actually the thing we're interested in preserving. But on the other hand, it also introduces some not so nice things visually, like this very well-known staircasing effect, that it also tries to approximate the image in areas where it should be kind of linearly increasing the intensity. It's also trying to approximate it with something piecewise constant. And that's really the interplay between this L2 discrepancy term that encapsulates my forward model and the regularization. Now you could think, well, for this linearly increasing stuff here, maybe I should do something like not sparsity in the gradients, but sparsity in the Hessian, which would be total variation of the Hessian. And then you get nice linearly increasing, decreasing stuff here. This is nice, but you kill the discontinuities. Then you can go further, and people looked at combining in an informal convolution way first and second order regularization, which is called this total generalized variation of second order, which kind of decomposes the image in which first order regularization is more appropriate and in regions where second order regularization is more appropriate. And then you get actually quite nice reconstructions. And you could go on. So the list is very long, and the point of all of this, of me telling you all of this, is really just to tell you that there is a vast zoo of different approaches of how regularizers are chosen. And this list for sure is also not complete. You know, many of you are using wavelets as a kind of dictionary for representing solutions to such problems and sparsity in relation to that. Apart from total variation, people have used all kinds of function spaces, Sobolev, Bezov. People have used PDEs also, which is, by the way, where I'm coming from, and many, many different types of approaches. Okay, so what I would like to talk about today is learning a regularizer, and this has something to do with the Wasserstein distance, and this will become clear in a few minutes. But before that, let me say that this is a joint work with Sebastian Lunz, who is a PhD student of mine, and Ozan Öktem, who is was somewhere, he's there. And let me really say that this is really the work of Sebastian. So it's really, yeah, it's really his, it's really owned by him, basically. Okay. So, so really the idea we started out from was to say, well, if it's so difficult to come up with good regularizers, and I mean, people have spent careers on designing different regularizers, so it's really a very difficult problem to capture, the vast variety of different types of solutions you might get from such solutions of inverse problems. So why not also think in this era of machine learning, deep learning, think about learning the regularizer from just feeding it with enough examples. And we have this kind of picture in mind that deep neural networks are somehow able to extract maybe some features that regularizers might also do in a certain extent or might represent. So maybe why not try to do something like this, and maybe we get a richer and more expressible type of regularization that covers a larger set of solutions and is more adaptive actually to the type of images we want to reconstruct. So this is somehow the idea. And I mean, this idea, just I shouldn't spend too much time here because I really want to go to using deep learning for this task. But this idea is, again, using learning in the context of, in particular, sparse reconstruction is not new. And here I just have a few keywords, which is, dictionary learning, sparse coding, this plug and play ideas. And then we looked a couple of years ago at this Bilevel type of optimization for learning parameterized regularizers. And then this is what I want to talk about today. Okay, so how can we do this by using deep neural networks? And I don't know if at that point you all know, you have a good understanding of what neural networks are. Yes? You have?
The whole morning talking.
So then I can skip this. I can skip this. So, but okay. So let me skip this. Thank you, Ron. Okay, let me skip this. I hope that was actually true. But okay. So what are people doing in this context? And so let me just give you a rough kind of overview of what people have been trying to do in the context of inverse problems and using deep neural networks in this context of inverse problems. Okay. So the first idea that comes to mind, actually probably to no one in this room, but to some people would be to say, I just learn this fully. I get measurements, I take images, ground truth images, and I learn the full process of, for instance, CT reconstruction. Okay? So that works. I mean, there was a really quite, well, I don't know. I shouldn't say too much because I'm recorded. So, so that actually arose quite a lot of interest, was published in Nature last year, where they used this to solve MRI reconstruction. Okay? And I would say this worked. They just needed a lot of training data. Okay? Because really just, if you think about it, they didn't just need to learn how to regularize in a sense, but they also needed to learn what to invert because they didn't even use the knowledge that there might be some type of Radon transform involved in the process. So then the other idea was, well, actually, really from the starting point that doing this might be unfeasible in certain situations, why not first kill the problem of being in a different space and do a first kind of simple inversion by, for instance, the pseudo-inverse, by applying the pseudo-inverse, filtered back projection in the context of CT, and then use the neural network in an after effect to kind of clean up, okay? To denoise and clean artifacts that are typically in this kind of pseudo-inverse type reconstructions. So actually, let me just go to the next slide and show you what I mean by that. So you apply the pseudo-inverse to your data. You apply the pseudo-inverse to your data. And then this is my kind of placeholder for a neural network. You take then this now image, and you send it through a neural network that is parametrized by theta to reconstruct you. Okay? Good. Another idea was to interleave the inversion and the neural network regularization step, and to say, okay, so I might initialize with my pseudo-inverse, but then I'm interweaving. I'm feeding the neural network not just with the last guess for my reconstruction, but I'm feeding it also with some information about the forward operator is given by the gradient of the discrepancy term. Okay? So I'm saying, basically what I'm saying is that I'm iteratively reconstructing, always feeding both in the information from the image and from the data space. Okay? And then you pick a certain number of iterations and you learn this psi theta, which can also, by the way, change with the iteration. Okay? Okay, so what we want to do is we want not to do something like this, but what we want to do is we still want to solve a variational regularization approach in the end and just learn the regularizer. So what we want to do is we want to learn the regularizer and then take it away, be happy with it, plug it into my variational approach, and then solve this, okay? For however long you want to use it, okay? And the idea is really the following. So why I, or some people, not just me, like variational problems is because the forward operator gets into the solution in a very explicit way. We can prove things about this, which I will show, I hope, if I have time. So we can prove things about the solutions. We can still play with the regularization parameter. So we can play with, we can adopt this to different types of noise levels. And it's quite flexible. So, I mean, now I'm telling you we are solving this variational regularization approach using this regularizer. You could also think about plugging this into some type of, or combining this with some type of EM algorithm or something like that. So this is roughly the idea, that we want to learn this regularizer. And how do we do this? Well, so I mentioned briefly before that one thing that some people have thought about, including myself, is to think about learning regularizer in the context of a bilevel optimization problem. So you parameterize your regularizer in a certain way. This could be parameterized by a neural network, okay, but by anything you want to parameterize this with. And then you take this variational regularization problem and you put it as a constraint into a minimization problem where your objective is that the minimizer of this should be close to some given ground truth, okay, that you have in your training set. And then you hope that you have many of those, and you look for good parameterization that in average works well for all of these images in your training set. Now, this in theory actually looks reasonable, but it's quite a tough optimization problem because you have, so it's called bilevel optimization problem because you are solving an optimization problem on two levels. Depending on how you parameterize this, this can be actually extremely tough to solve, okay? So we're not doing this now. What we want to do is we want to decouple the training of the regularizer from solving the variational problem. So this is roughly what we want to do. And how do we want to do this? We want to do this by not training the regularizer explicitly on individual pairs of ground truth and given measurements, but we want to train it in a distributional way. And I'll tell you, and this is where the Wasserstein distance, by the way, comes in, okay? This is roughly the idea. So the heuristics are, what I want the regularizer to do is I want the regularizer to not like the artifacts that I want to get rid of in my reconstruction. So I want it to suppress noise or other type of characteristics, so random noise, but also other types of characteristic artifacts that I know my inverse problem features, okay, like streak artifacts or something like that. So I want it to be large for these type of structures. On the other hand, I want it to be small for reconstructions that are close to the ground truth, so that I have structures that appear in typical images that I want to reconstruct. And so how do I do this now? So what I do now is I construct two different distributions. I said I want to train this regularizer in a distributional sense. I construct two different distributions. One distribution is the distribution of ground truth images. Okay, I call this PR. And then I construct a distribution. Let's just look here. I construct a distribution Pn by taking all the images that I get by applying the pseudo-inverse to my measurements. So now my argument is what I want my regularizer is to like images from PR and not to like images that come from the pseudo-inverse. So I want to construct a regularization that aligns the reconstruction with PR but takes it far away from Pn, which are my images, which is, the very simple reconstruction that gives me a lot of these artifacts that I want to avoid. And how do I do this? Well, one idea how to do this is via the Wasserstein distance. Now I have two distributions. How to measure their distance? Well, Wasserstein distance might be good. And in particular, so I look at the Wasserstein distance between those two. And I formulate now the Wasserstein distance in terms of the Kantorowicz duality. And so now I don't know how much you know about this. optimal transport stuff. But the main thing is if you look at this characterization of the Wasserstein distance between these distributions Pn and Pr, what I want is that my regularizer, my optimal regularizer, is the argument that gives me the value of the Wasserstein distance. So the argument that maximizes this difference here. Okay, so what's the incentive of doing this? So what I want, so my F star should be my regularizer, the optimal one. The incentive of this is that I want that F, when it's fed with images that come from this distribution Pn, then the regularizer should be large, we said, right? And if we feed it with images that come from this distribution Pr, then it should be small. Does it make sense? Now I'm maximizing, then I get this kind of property. Okay. Okay, so does this make sense? Okay, so yes, thank you for yes. And now I'll give you another argument why this might make sense. So what we somehow would like is, if we think about then taking this F star, plugging it into the variational approach, and then solving, reconstructing an image by solving this variational approach, what I might want is that if I take this variational model and take a gradient descent step in this direction of the regularizer, that I'm somehow, this regularizer takes me closer to my desired distribution, right? So let's imagine I do the following. I start with a sample from this distribution of pseudo-inverse reconstructed images, okay, the noisy artifact images, Pn. And I take U here, and then take from U a gradient step into the direction of this regularizer F star. And I construct a new distribution of these now G eta of U that I call pi eta. And so what this here just says is that when I do this, actually, this gradient step takes me closer to the distribution PR. What this means in the following sense, in the sense that the Wasserstein distance is decreasing when I take this gradient step. The Wasserstein distance between PR and Pn is actually decreasing. Okay? So this is kind of comforting. Now, and if you go back here, the question is how do you compute now this such an F? And here is where neural networks come in, okay? So now what I do is, in order to compute this, I just parameterize F with a neural network. This is the idea. And I need to do something with this constraint that I'll tell you now in a second. And so this, how to deal with this actually was not our invention. So this actually using the Wasserstein distance in the context of deep learning has been around now for like two years or so. In the context of generative adversarial networks, I'm not going to go there. But the idea roughly is that I'm approximating the maximization in my Wasserstein distance over all one Lipschitz functions. I'm replacing this by now maximizing this over all neural networks, all functions that can be represented by a particular type of neural network, parameterized by theta, that fulfills this one Lipschitz constraint approximately, okay? I'm taking this is called the Wasserstein-Gunn gradient penalty, okay? So I'm taking the constraint and putting it here into this loss as a penalty term, okay? This is right, this is for my one Lipschitz constraint. And now I'm minimizing this, and then the idea is I take the psi theta, I train this on enough examples of Pn and Pr, and then I take it away, plug it into my variational approach. Is this actually my next slide? Yes. Plug it into the variational approach and solve this, okay? Right, and then maybe solve this via gradient descenters or something like this. Okay. So one difference to the type of variational regularization approaches that I've shown you at the very beginning is, of course, well, first of all, what is this guy, right? This is very hard to understand what this actually is in the end. Also, in contrast to before, at least in the type of regularization approaches that we have been looking at, like total variation or something like this, or L1 of something, at least if the forward operator t was linear, we still got a convex problem. Now this is not the case anymore, because this neural network is very non-convex. Okay, so we have to pay a little bit for that. Okay, so how does it work? Now, what you see here is on the left, you see the ground. So this is again for computer tomography. Okay, on the left you see the ground truth. This is from a data set. I should have cited this here again. I've cited it at the beginning for the recording, please. I've cited it on the second slide. This is an online data set which is called Luna. And here you have 2 examples of this, ground truth images. And what we did is we simulated the measurements, the sinogram. And then this is the type of filtered back projection that you get based on how we simulated the data. Okay, so these are actually, if you look at this, these are samples, let's say could be samples from PR, from this distribution of ground truth images. And these could be samples from this distribution of the distribution Pn of pseudo-inverse reconstructed images. Okay, does it make sense? These we want to avoid. These we want the regularizer to actually favor. Okay, and we have trained the regularizer to do exactly this with this Wasserstein loss. This is somehow the idea. Now, what do you get with total variation? Doesn't look too bad. I mean, well, looks typically total variation like. This is what you get with post-processing with Michael's approach. So filtered back projection and then the UNet. Okay, and this you didn't talk about today, right? No. So Michael actually worked on the post-processing too. So this is what you get with Michael's approach, and this is what you get with. And actually here on the screen you can't see a lot of different. So we call it adversarial regularizer because it's trained in this adversarial fashion, right? So with P, N, and PR. This is what you get with the adversarial regularizer. So before I go to the next slide, it's hard actually to see anything really significant here. You maybe see a little bit that the adversarial regularizer really kind of focuses into one type of answer. So here, for instance, it tries to connect this in one particular way, versus the post-processing is introducing some kind of uncertainty, which actually in the ground truth is more suited, right? So yeah, so that if you look at how this works, in general, the table that you get is as follows. So maybe we can look. So first of all, it's clear. So these are the 2 learned approaches, okay? And these are 2 different quality measures that I apply on the reconstructions that I get. So peak signal to noise and structural similarity index measure. The higher, the better, okay? And okay, so the first thing I see is that the moment I use something learned, either the post-processing or the variational regularization with the learned regularizer, I get much better. Another thing that we see is that actually the post-processing is doing pretty well. So it's actually, on average, slightly better than doing the variational regularization with the learned regularizer. But note, and this is really an important thing for people in inverse problem to actually realize, I think, because this is one thing that I found quite cool about the adversarial regularizer. We call it here unsupervised. Why do we call it unsupervised? We call it unsupervised because if you think about the way we are training on the distribution PR and the distribution PN. These do not need to be paired. You don't need to have the same sample that you have in the ground truth connected with a sample in PR, right? So these could be disconnected. So actually, this could be nice in a lot of inverse problems where you don't want to compare things individually, and where you actually a lot of times don't have the ground truth for your real measurements. Okay, so but how does this function actually look like? Okay, so what is this regularizer? What is it? Is the question. What is this regularizer doing? And now here we can say something in an idealized scenario, okay? And the idealized scenario is the following. The main thing behind what is written down here is that I'm assuming there is a compact set, this what is called here the data manifold, a compact set N, on which has two roles to play. First of all, the distribution of ground truth images is supported on this weakly compact set M, okay? So I'm somehow saying my PR is not behaving totally crazily, okay? So it has some, makes some sense to group it somehow, to learn something for this overall distribution PR. The other thing I need is that the noisy data is not too totally crazy and far away from PR, which means that, again, in a distributional sense, if I take the distribution of noisy filtered back projected images, let's say, then I can use an orthogonal projection onto this manifold to get back to PR. Okay, so these are my two assumptions. Okay, so now if you accept those, if you digested those, then I can say something. I can say that one maximizer of this Wasserstein loss we can actually kind of understand, and it is the projection onto this manifold. Okay? This is actually what this regularizer, or one thing that this regularizer is doing, is projecting onto this manifold that is supporting this distribution PR. And now the other thing I said, and I'm not going into too much details here, the other thing I said was that I kind of like to stick with the variational approach because I can say something about this. And actually, when I say here theorem and we prove this, it's actually just application of standard theory, standard inverse problems, variational regularization theory. We can at least prove that a solution exists, and we can prove stability in a very, very weak sense, okay? So if we start with two Banach spaces, so X is the space for my reconstructions, Y is the space for my measurements, both of them are Banach spaces, then I can at least say that there is stability in the weak convergence sense, okay? In the weak topology of the Banach space X, where my minimizers lie, okay? So at least this I can say. And yes, okay. And what we are heavily using here is the one Lipschitz property that we get from the regularizer. So actually, I'll say only something very briefly about this, also something that Ozan and I are interested in. When does it make sense to have a regularizer? I said before, there's something really interesting for inverse problems people, that this regularizer is not pairing, that it doesn't need the pairs between the measurements and the ground truth images. Well, it's interesting in certain scenarios where actually what you want to reconstruct is also not unique in terms of it could be a rotated version of something, right? Like, for instance, in this single particle analysis. But I shouldn't actually talk so much about this because we still want to do some research on this and not others to do it. So, okay, so takeaway messages. So what I've talked about is really learning regularization in variational reconstruction approaches, thinking about it or setting it up in a way where we parameterize the regularizer in terms of a neural network. And the heuristic of training this regularizer was that we trained it to really favor ground truth images or structures that we have in ground truth images, and really unfavor or hate images from the type of very simple reconstructions like filtered back projections. And I don't want to repeat myself. I think I've talked a lot about advantages here. Let me actually say a few disadvantages. Maybe one thing I should say, really, which I haven't said, is you don't need a lot of training data to train a regularizer. This is also actually quite surprising. So you can train this on very small data sets. And the reason conceptually really is that in the end, you are solving a variational regularization approach where the data forward operator and the data come in a very explicit fashion. So you really have the regularizer as some kind of prior. Okay. Disadvantages. One reason why people in inverse problems, in particular also the ones who are solving these L1 type minimization problems for a long time, why people are interested in neural networks is because they're just, once they're trained, they're very fast. Of course, we are losing this because we are taking the regularizer and then solving a variation regularization problem in the end. So we still need to deal with computational complexity. And in comparison at the moment to things like post-processing, we do worse in terms of the quality measures. And with that, I thank the people without whom this wouldn't have been possible, so the people in the CIA, and I thank you for your attention. Thank you very much.